In this lecture, we're going to talk a little bit about the uniqueness theorem for equilibrium problems of elasticity. Basically, what that means is we're going to be ensured a unique solution under certain conditions. So, I'll put this in quotes here. If either the surface displacements or surface stresses are given, the solution of the equilibrium problem is unique for small displacement elasticity. So, let's first just remember what equilibrium is all about. So we have the partial of sigma x with respect to x plus the partial of tau xy with respect to y plus the partial of tau xz with respect to z plus a body force per volume term in the x direction is equal to 0 for equilibrium. And we have two other equations that are very similar to this. With our strain displacement equations and our stress-strain relations, we can use these as the basis of a set of partial differential equations to solve for the stress fields in a body. Okay, and what we're saying with this uniqueness theorem is that the stress fields and the displacement fields that go along with that we get out of this are going to be unique for small displacement elasticity. So let's recall what small displacement elasticity is all about. It's when we neglect the higher order terms, the deformation gradients. Epsilon ij is equal to 1/2 for the displacements, the partial of ui with respect to xj plus the partial of uj with respect to xi. If we have terms that look like normal strains, like epsilon 1,1, we would get a term that looks like the partial of u1 with respect to x1. If we have tensor shearing strains like epsilon 1,2, we would get terms that look like 1/2 partial of u1 with respect to x2 plus the partial of u2 with respect to x1. Now in this discussion, we're actually going to be talking about engineering shearing strains, and so we're going to be looking at terms that look like gamma 1,2 or gamma xy, if you will, which would be 2 times epsilon 1,2, which would be terms that look like partial of u1 with respect to x2 plus the partial of u2 with respect to x1. Alright, so we're going to talk a little bit about our strain energy density function. Right now, initially, we're going to look at isotropic materials. We'll talk about what happens for more general anisotropic materials as well. And then we'll get into kind of an argument about how and why this is unique solutions when we're given either surface displacement or surface attractions or stresses as boundary conditions, that we get a stress field that is an equilibrium for the body that is unique. So we know when we get a solution, we have the solution for that particular region. Alright, so in the recently preceding lectures, we talked a lot about our strain energy density function U, and one of the ways that we expressed it was in terms of principal strains for isotropic materials. Okay, so these are principal strains. And we have an isotropic material. And the lambda and the g are the Lemay coefficients. Now, if we know ahead of time that lambda and g are greater than 0, if those are positive, then we can take a look at this equation. Since these principal strains are squared as a grouping, and they're individually squared over here, then u is going to be greater than 0 if these strains are non-zero. They don't even have to be positive. but they can be, positive or negative, and the U is going to be a positive term. Okay. Now, the other thing we can see from this is U will be equal to 0 if and only if, it's usually abbreviated as IFF, if and only if each of these strains are identically 0. So the implication here is that the strain energy density function U is positive definite. Now there's another way that we can approach this. We can take a look at this in kind of a more of a matrix format. Let me get a little bit of room. If we express this 2 times our potential function U in a matrix form, so we're pre-multiplying by the vector transpose for the principal strains, we have a matrix full of these Lemay coefficients, and then post-multiplying by the vector epsilons, the strains, then we can find the eigenvalues of this matrix. And we can call these maybe S1, S2, and S3. So I'm just following along with our book. And if we find these eigenvalues, then 2 of them are going to be the same. Let's say the first 2 are equal to 2g, and then the second one would be equal to 3 lambda plus 2g. And if g and lambda are positive, then that also implies that E and nu are positive. And if we recall from another lecture that we actually found the normal, the usual elastic constants E and nu, modulus of elasticity and Poisson's ratio, in terms of Lemay coefficients as follows. And knowing that for engineering materials, and really any material that we know of, Poisson's ratio varies only between 0 and 1/2. Remember, we're talking about isotropic materials right now. Then we have E and nu being greater than 0 are necessary and sufficient conditions for U to be positive definite. Now we did start off talking about general anisotropic materials. And in which case we would have something that looks like this. 2U would be equal toCijkl, epsilon ij, epsilon kl. And then the conditions on being positive definite are controlled by determinants of various submatrices ofCijkl. And it's a little bit beyond what we're going to get into in our class, but if you deal with anisotropic materials then that use a potential function for linear elastic material behavior, then you may dig into these things a little bit. And if you use finite element codes and you're dealing with anisotropic materials, this is some of the basis for the conditions on how some of these anisotropic material relationships must be formed. So they will have some statement like nu xy whatever has to be greater than 0, or has to be in a certain range. There are certain conditions that have to be met from a theoretical perspective that they will enforce in their finite element code. It helps with a few features. It helps getting the right stress fields, but it also ensures this positive definiteness of our potential function. Alright, well, let's kind of go back to this idea of equilibrium. So let's write down our equilibrium equation again. This whole discussion is about uniqueness of the solution as termed by the equilibrium equation. So we know we have 3 of these equilibrium equations. They all deal with partial derivatives of the stress fields with respect to spatial position. And they look something like this. Well, the first one looks like this. Where the Bx refers to a body force per volume. Now it is in equilibrium, so we have the right-hand side equal to 0. More generally, we would have acceleration, but this discussion is focused on equilibrium. Now we know that we can take partial derivatives of a strain energy potential function with respect to strains and get stresses. So we can cast this equilibrium equation in terms of partial derivatives of the potential function u. So the stress sigma x, let's highlight this term, the stress sigma x is this term right here. It's a partial derivative of u with respect to epsilon x. And what we're doing is we're going to take the partial derivative of that term with respect to x. Likewise, we have some additional terms. We have the partial with respect to y of the partial of u with respect to the engineering shearing strain gamma xy. And we have the partial with respect to z of the engineering shearing strain gamma xz. And then we still have our body force in there right now. Alright, now here things are going to get a little bit confusing because of notation. And I apologize for that, but we're sticking with kind of what the book's using, and the book is kind of all over the place with the notation. Let me get a clean page here. Alright, so we're going to assume that we can have maybe a non-unique solution for displacement fields in a body. Suppose there are 2 displacement fields that result in stress fields through our elastic constitutive equation, equilibrium and compatibility, that satisfy our field equations. And we're going to call them U, V, and W prime, and U, V, and W double prime. Okay, now we use capital U for our strain energy density function. Now we're using little u as a displacement component in the x direction of our rectangular Cartesian field. Well, if we have these 2 fields that satisfy equilibrium, we can take their difference. And this is where just regular little u, we're going to call the difference between u prime and u double prime, and likewise for the others that we have here. Now where we're headed with this is we're going to show that when we have the u, v, and w that are the difference in here, the only difference that can exist is going to be a constant. which represents a rigid body displacement from some position. So otherwise the fields have to be identical within a rigid body displacement. Alright, so if we have these two fields and both of these two fields satisfy equilibrium, when we take the difference of these two fields' equilibrium equations, what we're going to get is the body term is going to be subtracted away. So, as we had just written down before, we're going to have the stress and the partial derivative of that for equilibrium. But now, this field is the difference between these two that may satisfy equilibrium. Okay, so when you read that in the book, it kind of looks funny because all of a sudden the body force term is gone, but it's gone because the two fields that satisfy equilibrium are subtracted from one another. Alright, now here's something else that's going to seem a little bit weird at first, but it'll make sense. Suppose we have these fields and this equation is satisfied. Well, if I multiply something by 0, I still get 0. And if I take an integral over that integrand that is 0, then that integral result should be 0. Okay, I am going to need another page for this. Alright, so I'm just going to say, then also, okay, now here's my volume integral. If I take a displacement field u and multiply it by this thing that's equal to 0, I need to let my stylus catch up here. There it goes. Okay, so if I integrate that over the volume, then it's equal to 0. But I not only have this equilibrium equation, I also have two other equilibrium equations. Now, I'm going to finally write down those other two equilibrium equations. We're going to take the v component of the displacement field, multiply it by 0 as well. But now we have tau xy in this term, which is partial of u with respect to gamma xy, and so forth. Okay, it's just going to take a moment to write all these things down. And then lastly, the third displacement component difference, W. And do keep an eye on my subscripts. It is easy to make a mistake on something here or there. But these are also in the book, and they looked correct in our book. Okay, so that integrand is 0, and so when we evaluate that over the volume as an integral, then that integral will be equal to 0. Okay, now let's keep that in mind for a moment, and we need to go back and talk about the divergence theorem. In fact, let me just pop open another window here so we can call this back when we need it. All right. So there's different ways to write the divergence theorem. The basic idea is that a divergence theorem can help us transfer volume integrals to surface integrals and so forth. So if we have a displacement field U, okay, now here's another confusing bit of the notation. This displacement field U has scalar components u, v, and w. But if we go del dot u dv, we can rewrite this as a surface integral of u dotted within the unit normal ds. Okay. All right, now let's say that this u has components u, v, and w. We can write this in terms of components as well, instead of in this kind of a direct vector notation. And so it has an expression like partial of u with respect to x, plus the partial of v with respect to y, plus the partial of w with respect to z, dv, that would be equal to a surface integral of the u component. Let's see, trying to make a capital U here this time, times the n1 plus the v component into plus the w component in 3 integrated over the surface. So n1, n2, n3 are the unit normal, and capital, well, let's see, let's do this. The u with the squiggle underneath of it is made up of the vector components of capital U, capital V, and capital W. Alright, now in the previous slides we've used capital U as a strain energy density potential function. Keep in mind that this U is different than that U. Alright. Now there's something else about the divergence theorem that we're going to draw upon, and that's when, instead of having the component U being just the function U, whatever that is, if that U was actually the product of two other functions, we can write the divergence theorem a little bit more differently. Now we haven't really made use of this so far in class, so this may look a little bit weird, but I even remember it from calculus, so I'm pretty sure this is something good. Suppose that U is equal to a product of A and B, and just for simplicity, right now we're going to take capital V is equal to 0 and capital W is equal to 0. So we're only going to focus on this first term that we have here. Alright, so if that U can be broken down as the product of two functions, then the volume integral of A, the partial derivative of B with respect to x dv, is equal to minus the volume integral of B, partial derivative of A with respect to x dv, plus a surface integral of A times B times the n1 component of the unit vector ds. Okay, again, the divergence theorem is a little bit more complex than we get into to derive that in this kind of class. We're going to draw upon this. But the reason why we want to end this form is that the equation that we just wrote down looks a whole lot like this first term right here. Let's make a little bit of room. Alright, so in here, we're only going to look at one of the terms for right now. The A term is the U term, and the B term is the partial of the strain energy potential function U with respect to epsilon x. Okay, so we're only going to look right now at this U multiplied by this term right here. Okay, so here we have the partial with respect to x of this term. That's the B, and then the U is the A. So that's the equivalence that we have going on here. Now we also have the idea of our strain displacement relations, and we wrote those down previously as well. Now we have similar expressions then we can do for these U times this term and this term, the V times these three terms, and the W times these three terms. They each give a contribution to a volume integral and a contribution to a surface integral. And then, like I said, along with the strain displacement relations, we're going to get a big expression. And I'm going to take my chances here and assume that I can write this all on one page. We have surface integral terms that look like this. The N1, the N2, and the N3 are the unit normal vector components. It's an XZ term there. And then we have our last line. Again, these are all in terms of partial derivatives of the strain energy density function. Okay, and that's all integrated over the surface. So that's the second term that I have here, the A, B, N1 type term. And then we have another term that's going to be the volume terms, and it's like the B partial A with respect to x, dV type terms. Except now we're going to have the partial of U with respect to x. And since we have partial derivatives of U with respect to x, that's like a strain term epsilon x. Okay. And likewise, we will get similar terms for the other two normal strains. And we will get contributions that add together to look like shearing strain terms on the mixed partial terms. And almost got this done here. And that is over the volume, and then this whole thing is equal to 0. Alright, so now we have a couple things going on here. We can have surface displacements going to 0 on a certain surface region. If the surface displacements go to 0, the u, v, and w terms go to 0. And that surface integral evaluates out to be 0. And we're left with the volume integral. Alright, there's another thing that can happen, is that the stresses from the little u, v, and w if those are prescribed, the stresses are prescribed, the tractions on the surface S, those stresses from little u, v, and w will also vanish, because u prime, v prime, and w prime, u double prime, v double prime, and w double prime give the same solutions. Alright, so let's write a little bit of that down. Let me put the equal to 0 up here somewhere. Let's see. The displacements may be controlled. So the surface integral vanishes. Or the stresses from u, v, and w vanish. So that would be the partial u with respect to epsilon x terms. All of these terms will go to 0. Since u, v, and w is the difference between two states, two displacement states that give the same stress field equilibrium equations. U, v, w prime and u, v, and w double prime give the same solutions. Okay, so in either case, what we're going to be left with is that term in the brackets. This should be a square bracket here. That term in the brackets has to be 0. That term in the brackets, well, that is 2u. Now the only way that u can go to 0, the integrand is going to have to be 0 if the volume integral is equal to 0, because we have an arbitrary volume integration. Is if the strain fields give us the principal strains all equal to 0. And the only way that the principal strains can all be equal to 0 is if we don't have any difference in the deformation gradient terms. That only happens when displacement fields are differing by a rigid body displacement. Alright, so let's write that down. Okay, now I'm not saying that any old displacement field is a rigid body displacement. What I'm saying is if we happen to have two solutions of displacement fields that satisfy equilibrium equations, then the only way that can happen is that the difference in those two displacement fields, the only difference there can be is a rigid body displacement. So in the end, what we're saying then is that the equilibrium equations, a solution to that differential equation that satisfies the equilibrium equations, will be unique. Now, the result I don't think is very earth-shattering. We have linear problems, and the solution to any linear problem should be a one-to-one correspondence, should be unique. But this kind of goes through and shows more formally how we can think of this in a very mathematical way. We don't want the math to get in the way of what we think we need to do, but sometimes the math can give us further insights into different things. So saying that the displacement fields are unique for a given elasticity solution also has some implications to our material behavior assumptions and their stress-strain relations. So if we find this, we don't have to go hunt around for another set of strain fields that also satisfy equilibrium. Once we have it, we've got it. This is not the case for things that behave like nonlinear plasticity. In nonlinear plasticity, we can have the same strain field developing from different stress fields. There's a path dependence, and we have plastic dissipation and different things going on where we're expending energy. So that's what I want you to get out of this, is to understand that once you have a nice linear elasticity solution, small strains, small displacements, then that solution is unique.